All right, so we have one last section to go through in Chapter 4, and that's getting back to Newton's laws. So we've already talked about Newton's first law, and Newton's first law is the law of inertia, where an object at rest tends to stay at rest, and an object in motion tends to stay in motion unless an outside force acts upon it. Newton's second law, we came up with a formula that acceleration is the net force divided by its mass. So force causes an object to accelerate, and that acceleration is directly proportional to the mass. Inversely proportional to the mass and directly proportional to the force. And now we're going to get into the third law, which is commonly referred to as the action-reaction pair law. And we'll take a look at that right now. So I'll do a quick little demonstration in class, and I'm going to have two people with force plates. They're plates that can get pushed on, and they measure the force in newtons, and they are calibrated and zeroed out, and they're going to push at each other, and one person is going to push onto the other one, and my question is, who experiences the greater force? So let's say that there's this big person here, and they got this force plate, and then there's like a little person here, and they got a force plate, and this big person is pushing and pushing and pushing, and let's say, for example, that they end up going to the right. And my question is, who experiences the greater force? And we intuitively want to say that this person experiences the greater force because they're moving to the right, they are being pushed around, they must be experiencing the greater force. And the reality is that's not the case. We'll see from the force versus time graphs that they actually experience identical forces. And it's a really, really weird concept, and people always struggle with, because why would they experience the same force? And the answer comes into Newton's third law. So Newton's third law is that motion will often involve two or more objects interacting with each other. So for example, I have a hammer, and it's hitting and it's driving down a nail, but we're saying that with that there's this reaction pair of the nail resisting or exerting a force back on the hammer, and we're saying that they are the same. Same thing if a bat hits a ball, your foot in a soccer ball, and the earth and the moon, there's all these action reaction pairs. They involve two things happening or interacting with each other. Now, the interaction of objects it's the mutual influence that one object has on the other object. So right here we have A and B. They are B is pushing to the left on A. So B is exerting a force on A, but A is also exerting a resistive force on B. There's an action-reaction pair. An action-reaction pair, when dealing with forces, they exist as a pair or not at all. There has to be two forces. So there's this force of B on A, and then there's this resistive force of A on B. And that is what Newton's third law is getting after. So Newton's third law states that every force occurs as one member of an action-reaction pair of forces. So we're going back to the hammer on the nail. Then there's a force of the nail on the hammer, and there is a force of the hammer on the nail. Each force is a different object, but the members of the pair point in opposite directions but are equal magnitude, as we will see in our demonstration. So they're two different objects, but they're opposite directions but equal magnitude. It's a pair of forces. We actually see this in nature too, in that in order for you, for example, to walk, the floor needs to have friction. So you're pushing back on the floor, and the floor is pushing forward on you, and that's how you're able to go forward. The friction that actually is stopping us from slipping is static friction, and we've all been there when we're on ice or some other type of slick surface where the friction isn't high enough and we walk forward and we slip and fall. The static friction has to point in the forward direction to prevent your foot from slipping, because otherwise there would just be a net force to the right and nothing would counteract that. Same thing with a tire on a road. It also brings us into this concept of like rockets and that thrust force that we've been talking about a little bit in class. The rocket itself pushes hot gases off the back, so it has a force going down, but it allows the rocket to go up because of that action-reaction pair. So I got a quick check. A mosquito runs head-on to a truck, which is true about the collision. We like to say that the truck exerts more force than the mosquito because the mosquito is getting smushed. But the reality is the mosquito and the truck exert the same force as on each other. And when I think about that, going back to my concept that acceleration is F net divided by the mass, okay? The mosquito has a really, really small mass and therefore a really, really, really large acceleration. The truck has a really, really, really large mass and therefore a really, 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 really small acceleration. And that's why we can justify that the net force is, in fact, the same. A little follow-up question would be, what is the last thing that goes through a mosquito's head during a collision? And the answer, of course, is its butt. Yeah, so that will actually end our quick little introduction into Newton's third law, but we will have some additional conversation about it in chapter 5 and a couple of the applications behind it. So there is more that we can talk about, but that's just that quick little introduction. Forces occur as pairs. There's an action-reaction pair, or they don't occur at all.